A prosthetic arm replaces the bones of the ulna, radius, carpals, metacarpals, and phalanges. Also, it replaces the muscles of the brachioradialis, flexor carpi radialis, the extensor carpi ulnaris, flexor carpi ulnaris, and the extensor digitorum. The earliest history of prosthetic care goes way back to 500 BC, which written references indicate that a Persian prisoner who escaped from his chains by cutting off his foot later replaced it with a wooden substitute. In 1812, an arm prosthesis was developed, which produced movement in the arm and hand using straps connected to the opposite shoulder. In 1945, the National Academy of Sciences established the Artificial Limb Program, which promoted and coordinated scientific research with the goal of improving the design of prosthetic devices. Many doctors and engineers work together to investigate the movement of normal human limbs so that the prostheses could be designed to appear as lifelike as possible. Now they understand biomechanics better and use computer-aided designs for the creation of new prosthetic devices. In the present day, the main material used to make a prosthesis is plastic polymer laminates such as acrylic, epoxy, and polyester that have a great deal of control over strength, stiffness, and thickness. Scientists have successfully transplanted sensory and motor nerves from the amputated hand to the chest so that the users can control the prostheses by thinking about moving the non-existent hand. Also, users can have a little bit of sensors on their fingers that transfer tactile information from the device to the chest. Both the creators and the users try to solve many complications of prostheses in order to implant the device as easily, comfortably, and pleasingly as possible. An article written by the Department of Pharmaceutical Sciences at the College of Pharmacy summarizes some complications that are involved with prostheses. First, the prosthesis needs to be biomimetic. Since the device is replacing a former biological part of a body, the transition and the movement need to be smooth. Second, implanting prostheses also means involving electronics and chips for signals and control. Thus, not only does the actual arm need to work well, but also the electronics that send the signals from the human to the artificial arm as well. Third, the materials of plants come in contact with tissues in the area that can cause different reactions. Of course, it takes time for the users to psychologically and physically adjust to the new prosthetic device. That period of time needs great effort, endurance, and patience. But of course, when that time is over, the user feels much more pleasing and relaxing. There are general challenges that a user needs to overcome, such as working through the feelings about losing a limb and deciding to rebuild his or her life after amputation, exercising to build the muscles needed for balance and ambulation, preparing and taking care of his or her residual limb to attain a proper shape for the prosthesis, and learning proper body positioning. Numerous scientists are working hard to make more development and improvements. For instance, at the Johns Hopkins University Applied Physics Laboratory, a team has just finished the most realistic arm model called the Proto 2 this year. This new design contains the injectable myoelectric sensor that detects muscle activity and wirelessly transmit commands to the prosthetic arm. It also performs 25 joint motions that make the elbow to flex and the fingers and the thumbs to bend at each knuckle. Each joint is brought together by bones made of carbon fiber and aluminum alloys. Now the scientists are working towards next steps that include shrinking the battery, developing more efficient motors, and refining the bulky electrodes used to read electrical signals in the muscles. For instance, the scientists are trying to explore a hydrogen peroxide pneumatic system to replace bulky, slow, and weak electric motors. Prosthetics users do gain an unfair advantage by competing in regular athletic competitions. The International Association of Athletics Federations reported that mechanical advantage of the blade in relation to the healthy ankle joint of an able-bodied athlete is higher than 30%. Furthermore, the prosthetic users use about 25% less energy than average runners. The scientific and mechanical contribution to make lighter, stronger replacement of a human limb is cheaper.